Welcome back, class. Tonight we're going to discuss heat transfer and thermal expansion. And today I showed you some demonstrations in class. This should help solidify what we discussed in class and help you understand a little bit more about heat. Now remember, heat is a flow of energy from a hot substance to a cold substance. And that always results in the colder substance increasing its molecular kinetic energy and the hotter substance decreasing its molecular kinetic energy until the two substances have equal amounts of average molecular kinetic energy, and that is when they reach thermal equilibrium. So today we're going to learn about how heat transfers. And there are three ways. The first way is through conduction, and this is a quite common way. Heat transfers through molecule-to-molecule contact. So here we have a candle with hot gas, okay, and that is conducting energy, heat through heat, to the molecules of this metal bar. This could be a frying pan or anything, doesn't really matter, but in this case it's a metal bar. So we can see that the molecules that are in contact with the hot gas, they increase their temperature. And as time passes, these molecules, through molecule-to-molecule contact, will conduct heat through the actual bar itself. And so we can see this, the heat would spread through the bar. And you know this, if you've ever held a frying pan over a stove, if it had a metal handle, you can only hold the handle for a certain amount of time before the handle gets too hot to hold it. And that's because the energy from the hot gas is being transferred through conduction. And so examples would be a frying pan on a stove or touching a hot object. Anytime you touch an object and you feel a temperature difference, that's going to be conduction. And today in class we cooked popcorn via conduction in the popcorn maker, where we had hot oil and a heating element, and you could do that on your stove. We also have convection. Now convection is a special form of heat transfer that only occurs in fluids, and it occurs because hotter molecules rise. So when you boil water on a stove, the energy transfers from the hot gas to the metal frying pan, and the metal pan then conducts energy to the water. So we get conduction there, right along in this surface here, where the hot gas is touching the metal and the metal's touching the water. But now when those water molecules warm up, they become less dense. Remember, they expand. We're going to talk about that in a little bit. They rise, and cooler molecules take their place and receive energy through conduction. So convection is this movement of hotter molecules, where the hotter molecules rise and the cooler molecules take its place. We also talked about this happens at the beach, where during the daytime, the air is hotter over the land, and that air rises, and then cooler air from over the ocean rushes in to take its place, and we get a sea breeze. And during the nighttime, the air is actually a little bit warmer over the ocean. That air rises, and cooler air over the land takes its place, and we call that a land breeze at night. So we see examples of convection in boiling water, also in the air in our atmosphere. And some of you also had an example today of convection ovens also can have heat transfer through convection. If you have a convection oven, you have a fan that circulates the air, circulates the hotter molecules. And then we have radiation, and this is the only way we can get energy from the sun, is energy that transfers in the form of waves, and that is radiation. So anytime you step into sunlight and feel heat from the sun, anytime you step in front of a fire or in front of those heat dishes at Costco, those special satellite dish looking like heaters with the orange filament in the middle, those are all examples of radiation. Okay, so anytime you feel warmth from any of those things, that's radiation. And we cooked popcorn today via radiation in a microwave. Microwaves are waves that can travel through space, and they also are what vibrate the water molecules in any food that you put in a microwave. The microwaves actually resonate with the water molecules, and then the longer you leave something in a microwave, the more the water molecules increase their vibrations and the hotter they get. So that's how you cook in a microwave. And then I forgot to tell you, but back to convection for a moment, we cooked popcorn via convection in an air popper. So that's what we were learning about today. Now, before that, we actually learned about thermal expansion. And so when objects heat up, when objects increase in temperature, the molecules vibrate around more. And when they vibrate around more, they take up more space. The actual molecules themselves don't expand. They just vibrate around more and take up more space. The object expands. And so as temperature increases, molecules vibrate more and take up more space. That's thermal expansion. All right? And it turns out the longer the object is, the more it will expand. The shorter an object is, the less it will expand. And that's very intuitive. So we see here that this object, as we've left it over the candle flame, expands. All right? And this expansion is directly proportional to the magnitude of that dimension. In this case, the length. So what we looked at today was a hoop. We heated up a hoop. And it was a metal hoop. And I asked you if that inside diameter would increase, decrease, or stay the same when we heated it up. So why don't you think about that for a moment. Would this inside diameter right here, as this metal hoop is heated, as its temperature increases, would that inside diameter increase, decrease, or stay the same? And of course, if you were in class today, you know that that inside diameter actually increases. And here's why. The thickness of this hoop isn't nearly as large of a magnitude as the diameter or the outside circumference. In other words, there are a certain number of molecules from the inside diameter to the outside diameter. Let's say 1,000. There are many, many more molecules that go around this outside circumference. Could be hundreds of thousands. So if each of those molecules vibrates around and takes up more space, as the temperature increases, then the circumference is going to increase much, much more than the thickness. And so that inside diameter would actually get larger. So here we see that. The inside diameter is getting larger because the circumference is increasing. Now the thickness is increasing a little bit, as you can tell, but it's not nearly enough to compensate for that much bigger increase in circumference. And so the inside diameter of this hoop would actually get larger. And the point of this is to understand that the longer the dimension, in this case the circumference, is much larger than the thickness. The longer the dimension, the more expansion that occurs. Okay? So we're going to be applying this more in class next week and applying this more to heat engines as well. Have a great week, 3-day weekend. I'll see you on Monday.